I'm Dr. Krishna Vasudevan from Electrical Department, and we will be first looking at the subject of electric actuators for the purpose of robots. Right? So, let me write that down. So, let's look at actuators then. That's what we are going to talk about. Actuators are essentially elements in the system, to create motion, right? There are, of course, various ways in which you can get actuation. There are hydraulic actuators, there are pneumatic actuators, and there are electric actuators. Apart from, these are the main varieties of actuation systems that are used in industry, and maybe you would have studied about some of these earlier. Now, of course, when you look at the area of robotics, one needs to pay attention to the needs of the domain of robotics and choose actuators that are able to meet the application need, right? So let's start with some examples of robots. I'm sure you would have seen or heard or whatever about various applications of robots. Can you suggest some? Where have you seen the use of these kind of systems? Drones, yes, drones are one widely used variety of remotely operated systems now, and we had a very famous example of a drone attack a few days ago. Yeah. Anything else? Industrial robots, can you be more specific? Industrial robotic arms for what purpose? Pick and place robots are one of the most frequently used in industry. Anything else? Assistive devices. Assistive devices in the sense, can you be more specific? Prosthesis. Yeah, they are assistive devices, yes. So you would not really call them fit them in the group of robots, because when you say robots, you are talking about more autonomous systems, right? Any other examples of robots? Mobile robots used for what? Application? Terrain mapping. Okay. Modular. Can you be more specific? What do you mean by modular application? Modular. That is, you are saying building their own shape. Okay. You have robots in medicine that can perform surgery. remotely operated. Yes, they are definitely remotely operated. Not yet, we are not yet in a state where you can leave yourself to robots and then, be under their discretion. So these are all many of the systems that are there, and certainly, there are lot of need for remotely operated systems. So remotely operated systems, for example, could be army vehicles, armored vehicles, where you want to send a remotely operated vehicle into the enemy domain and do some sort of surveillance perhaps, which is, you have already listed the example of drones, which do that, but drones are for aerial survey, whereas you may have remotely operated armored vehicles on land which do the same thing, which enter into an enemy domain and do some kind of, information that they can get. So, in all these situations, the goal is to have some sort of autonomous ability, probably remotely supervised, approaches. And if you look at the design of all these kind of systems, one then looks for, so if you look at all these applications, it is important that they are having movement, which is the essence of having a robot. You want it to achieve something, and since you are looking at this kind of an application, it is necessary that size of any system that is used on board, size must be reasonably small. Of course, ideally you would say that I want it to be as small as you can, maybe no size at all, zero size, and achieve some actuation, but that of course is impossible. So you would do with the best feasible kind of system. And if you have applications that are not going to be something that requires movement physically from one place to another, if you take, for example, industrial systems, industrial robots, we had one variety which was mentioned, that is equipment that are going to take some object and then put it somewhere else. So these mechanisms don't move from location to location, they are stationary, and the objective is to move an object from one place to another. So they have a robotic arm that gets hold of one object and then shifts that location to some other location. The robot itself doesn't move. But on the other hand, you have other applications. For example, if you look at the aspect of material handling robots. So here the idea is that you may want to shift some material from one place to another which is a long distance away. So you have a system, you may have, there are various ways of achieving this. One could be a sort of box like thing with a wheel here and the object that is located here, and this box moves wherever it needs to go. I'm sure you would have seen these kind of applications as well, right? So applications in industry are for a variety of things, and then you have also applications for underwater robotics, right? So you have systems that go underwater, look at the environment there, maybe attempt to attempt to locate something which has accidentally fallen or submerged, so on, right? So in all these kind of situations, you need size to be reasonably small, because if you are going to look at a system that is moving, obviously anything that is going to move has to shift itself first, apart from whatever load is going to be there. So you don't want the actual system itself to be extremely heavy. You want it to be able to take a load which is heavy. On the other hand, if you have these kind of systems, you are not really concerned so much about how big it is, because all the while it's going to stay in one place, and therefore you may have a little bit of leeway in sort of selecting the actuators and selecting the other system. So one important thing, as I mentioned, is therefore how big the system is. The second important thing is that your system should meet operational needs. There is no use in having a system that is small but it can't meet the load requirement. That is, if you want to lift this phone and put it there, you need to lift a certain weight. For that, you need to have a certain actuator of a certain capacity, and that has to be moved. So the actuator must be capable of accommodating a movement which makes the arm move from one place to another and then put it there. So the range of movement is important, speed of movement is important. All that is going to decide how much is the capacity of the actuator. And then you don't want to have an uncontrolled system. You cannot have an actuator fitted and say you do what you want, right? So you need to have an ability to determine how this system is going to actually move instant to instant, right? So you need to have an actuator that has very good ability for control. Right? So all these three aspects, 1, 2 and 3, are major aspects in determining what sort of actuation system you want. Right? The other important aspect is any actuation requires energy. Right? Without a source, you cannot achieve any movement. And therefore, you also need to look at what kind of sources are available, sources for energy. What sort of sources are available at a particular location for a particular application that you can make use of, right? So, if you look at examples for this, let's say you have an industrial robot which is stationary. One other use for an industrial robot which is a fixed location is robots used for welding. Have you seen that in assembly lines, especially if you go to automotive industries? Assembly lines are filled with these things, robots that bend in all kinds of forms and then apply the required amount of weld, right? If you look at these kind of applications, they are always located at a fixed place in an assembly line. They don't need to move, they don't need to do anything else other than bend their arms in ways that are determined a priori. You don't go every time and tell the robot move like this, right? So somewhere it has been decided a priori that this robot will start with its arm in a particular position, then move through few angles and rotations and all that, and then go and stay there for some particular time until the weld process is over, and then come back in a certain way, right? So these are, since they are always fixed in a particular place and the industry is filled with electrical electrical sources, in the sense electricity is available everywhere, it is most appropriate to build this out of electrically actuated systems. Electrically actuated in the sense, at least the first source of actuation could be electricity. The end result could still be achieved using something else. So there are actuating elements known as electro-hydraulic systems. Right? So they are essentially hydraulic systems, but the first level of actuation is by electrical means. So the electrical entity, the electrically actuated entity, then releases a flow of oil, and that oil is the one that ultimately results in the movement of the arm. Okay. So it may be electro-hydraulic, but then the initial form at least may be electricity, because it's widely available. But on the other hand, if you look at an underwater robot, how do you actuate this? That's very difficult, right? You don't know at what depth you are. You are not going to get a fixed amount of this thing at all. Initially, there is no pressure when you are on the surface, and as you go down, you get increasing amounts of things. So that's very difficult. Anything else? Battery is probably the best bet as of now, right? Otherwise, you could have some kind of oil, fuel, diesel, etc. stored within that, and then operate an engine, which will then give suitable actuation to whatever you want to move. Right? That's another option, but I don't think they are used in this underwater application. You don't want to take fuel all the way down, right? But in majority of the situations where the depth is not very high, right, they don't use the storage mechanism at all inside. They are simply having a long lead of electrical supply which is going to be available on shore or on board, and you simply make a long electrical link to the underwater robot, and it draws electricity from the shore, right? So this could be a way in which to do it. If you want, of course, autonomous operation, then you need to definitely have some kind of storage mechanism on board. So that is what you have. Here you have, as I mentioned, industrial electrical supply. Then I mentioned remotely operated armored vehicles. In this case, it is remotely operated. That means you are looking at an armored vehicle located somewhere, and then you are going to be sitting far, far away inside your own area, and this remotely operated vehicle is going to go into enemy domain, and you need to operate it there, which means that it's impossible for you to have a long electrical link for several long distances, and therefore there must be a local energy storage, and this is an armored vehicle. Therefore, the best form of energy storage will be fuel itself. So in this case, what you have on board is basically diesel engine, but this engine has to first of all move the vehicle. That is one thing. Apart from that, the vehicle may have a lot of other accessories for detecting many things. You may need to detect whether you have any explosives located underground, for which you need some sort of sensor, and those will need to be actuated by some arm, right? So you have to lift the sensor and then maybe locate it adjacent to ground, move it a little bit maybe, right? So there are further actuation needs for moving other accessories that are located on board, right? So how does one move that? Ultimately, the source of all that may be from the diesel engine. So in these kind of applications, usually the way it happens is This then is used to generate electricity, and then that is used to operate whatever else you may want to operate as an electrical accessory, right? So there are various forms in which energy storage or energy usage could be available, and one needs to select the appropriate mechanism for that. Now, if you look at this aspect, ability to have a good control, so you need to have systems where it can respond the way you ask it to. If you look at the way systems are, designed today, most of the systems that require some sort of control depend upon electronics, right? You want to write some software, you have some algorithm which you know, which you want to implement, which says that this arm should move from this to this location through this path with certain velocity profiles, etc. So this is an algorithm, and the easiest way today to implement an algorithm is to implement it in electronics, some digital electronics, FPGAs, MCs, so on, right? So this is exactly what you have, and electronics forms the basis of implementing very sophisticated algorithms. And once you have that, you may then use the end result of your algorithm, which is available in electronics, to actuate a non-electronic system. That is fine, but it's easier if there is an electric system at hand which you can control. And it so happens that when you look at actuators that you want to control, as of today, the actuating systems that give you the best ability for control are electric systems, right? So from that viewpoint, you have electrical actuators as the best means that is available. And then if you look at systems that meet the operational need, you need to select a capacity of the actuator that is appropriate for the particular use at hand, right? Which means that if you want to lift this phone, you need a certain capability from the actuator. If you want to lift this entire bench, obviously your actuator needs to be bigger, right? So one needs to select the size and the capability accordingly. There also you find that electric systems are fairly good. It means that output, or not really power, the mechanical torque that it is able to generate divided by the weight of the system is what is going to determine the efficacy of a particular actuator that you select. And electric actuators are not very bad in this case. They do fairly well and are able to meet most requirements. However, if you look at this number and you want to select the best out of the lot, you will find that hydraulic systems offer the best option amongst all varieties. They are usually the smallest for the output load capability that you want, right? So if you look at the earlier days, right, when actuation systems were required, they were invariably hydraulic systems, right? But the world is sort of moving away from hydraulic systems, mainly due to the fact that hydraulic systems are difficult to maintain. That's a big nuisance. You have to have oil which is high pressure, and then that oil has to circulate through lot of orifices, and you have to maintain the oil to be highly consistent, no dust, etc. And you have to take care of leakages, which will make operation very difficult. So because of all these things, people want to move towards electric actuators, which are much easier to maintain and operate, right? So due to all these kind of situations, so if you look at the first one, hydraulic are the best as far as size is concerned. but due to other things that we just now discussed, people want to move towards electric actuators. So, if you then look at electric actuators itself, electric actuators are today mainly electric motors. There are sometimes other valves that are used, electromagnetic valves, which can either release a fluid flow or stop a fluid flow. But unless that is the goal of that is the operational need at hand, mostly one looks at electric motors. And when you look at electric motors, one needs to take recognition of the fact that what is the source of energy that is available, in what form. Electricity, you know, that is available, electricity is available as either DC or AC, and one may at the outset say that I would choose a motor that is appropriate for the form of the source. If you have an AC source, an AC motor, a DC source, a DC motor, that approach works well if you want to look at very small applications, right? So, if you look at electric motors, I'm sure you would have all at least had some initial introduction to electric motors. So, electric motors are basically electromechanical energy conversion devices which then accept an electrical input and deliver a mechanical output, or this is the mechanical side of things and this is the electrical side of things. And an electric motor therefore enables an interaction between these two sides. Okay, the electric motor or electric machine in a more sort of generic sense is an appliance or a device that can take electrical energy and convert to mechanical, or take mechanical and convert to electrical. Both ways are feasible for any electromechanical device. And this interaction happens in that is enabled by the presence of a magnetic field inside the system. So, unless you have a magnetic field, this interaction doesn't happen. First of all, you need to establish the field inside the system. So, if you have such a system, then it is feasible to control the electrical side and get what you want on the mechanical side. Ultimately, as far as robots are concerned, you are interested in the mechanical side of things, and to achieve what you want, you need to have a good ability to control the electrical side of things, right? There are many different varieties of electric motors that are available. So, broadly, these motors are called as, one is DC motors and the other is AC motors. In AC motors, there are different varieties. One is called as the induction motor. Another is the synchronous motor. In synchronous motor, there are other varieties which are called as brushless DC motor, permanent magnet synchronous motor. There are yet another group of machines which are known as variable reluctance machine. So under this group, what you have are stepper motors and switched reluctance motors, and nowadays there's another variety which is also making its appearance, that is called synchronous reluctance motor. So these are broadly a large range of available electric motors for use in your actuation, use for actuation. Now the question is, which one will you use? Right? Now if you look at the need for actuation, I said earlier that any system that you are going to select must meet the operational needs. What do you think will be an operational need? From the actuator, what do you think will be an operational need? Torque requirement is a primary need. So torque capability is a primary need. Any sort of movement requires you to generate a force, which in the case of rotating systems is a mechanical torque. Now, if this is what you need, let me give you two examples. Let us say that with respect to time, I am going to draw a graph of mechanical torque. Actuator 1, okay, gives you, this is t equal to 0, that is when you start, which is when you start the actuator, and you find that the mechanical torque goes like that. Right? Let us say it is able to generate a mechanical torque that looks like this. The next case, I have another actuator 2. This is torque again. The next actuator generates a mechanical torque that looks like this. Which one will you choose? Why do you use the word stable? Okay. So there are oscillations. I don't know whether it is reason enough to call it as unstable, right? But yes, so you think that the first one is better? Why? How do you think that the oscillations in the second one will impact your operation? There will be vibrations. Object may have some damage in a few cases, but what does it see? You said that there may be vibration. What determines whether vibration will be there? Definitely this mechanical torque is having oscillation, fine, but is it going to imply that you will have vibration? Is there anything else between this and the vibrations that you will see? Is there anything else that is going to determine how much vibration will be there? Damping is an important aspect. You are going to have an actuator that is generating this, But in order that this results in the vibration of a system, there are certain other elements in between, right? For example, if you take the case of a robotic arm, let us say I have a robotic arm that is going to pick up this and place it there. And in my arm, I have a actuator that in the first case moves like this, second case is that way. The first case is obvious. There is no difficulty. There is a smooth mechanical torque. It goes and settles down there. Now, in the next case, there is a slight oscillation that is there. So, how do you think the system will move? Is it going to really move like this? Whether you have damping later. So, the actuator that is sitting inside at the place which is going to have a rotational motion, that is the one that is having this kind of a mechanical torque, and the motion is not of the actuator but is of the arm, right? And between the actuator and the motion of the arm sits your mechanical system equation, right, which contains a lot of mass, and therefore there may be a moment of inertia which reflects onto the actuator, and that moment of inertia and the motion of the arm and your weight, etc., will mean a substantial attenuation of this ripple even if there is no damping, right? A substantial attenuation of that ripple may be there in the actual motion that is felt, right? It depends on the natural frequencies of the system. It may. So, exactly. So, there are these undesirable things. The question is how much, right? There is likely to be losses in the system due to this, right? There may be undesirable resonances that may happen. The question is at what frequency, right? So, if this oscillation frequency is kept far, far away from your mechanical system resonance frequencies, it's okay, right? As long as it doesn't cause an undesirable oscillation in the rotor speed itself. Definitely, let us say you have another actuator, a third actuator, which is generating something like this. How is this different from the second one? Higher amplitude, lower frequency, right? So, which one do you think is more is a little more difficult? Is it the third one or the second one? Third one. Why? Because amplitudes are higher, definitely. Then it can match the mechanical frequencies of resonance. Usually, mechanical resonance frequencies are low frequency. You don't look at mechanical resonance happening at 100 kilohertz. Never does that, right? If you want 100 kilohertz resonance from a mechanical system, you are looking at nanoscale or very, very light system, which is unsuitable for robotic application, right? So, mechanical systems, when you look at it, usually they are mass, weight, and therefore resonance frequencies are fairly low, right? Therefore, the last system that I drew is more likely to cause difficulties in your operation as compared to the second one. So, given a mechanical system, right, you can always therefore determine what kind of frequencies are allowable in that system such that it does not cause a difficulty. You must look at the fact that we are looking at an engineering application and not a physics application. I mean, if you look at just analysis and say physics, if you want an output equal to x, you are looking at x dot 0 as the output. But when you come to engineering, if you say you want an output of x, you are looking at x plus or minus something, which is acceptable to you, right? So, acceptability is what is of interest, not the fact that it should be exactly equal to some number. For example, if you say that this mechanical torque I want to be equal to 50 Newton meter, as an engineer, you would immediately ask how much is the accuracy, right? Do you want it to be 50.00000 or is it 50 with some allowance there, right? So you always say plus or minus some delta, right? So if this is the requirement that is physically achieved, you can always say, depending on your application, I want this value to be equal to 0.1 Newton meter. Maybe the application requires that, or maybe the application requires 0.01 Newton meter, right? But it's never equal to 0, right? So you have always a certain allowance in your application, which can then determine how much of ripple magnitude is allowable, right? And then comes the question of how much ripple frequency is allowable, which is then a consideration based on your mechanical system design. So based on that, one can allow. Therefore, we are now saying that it is not necessary to have this kind of a system. If you get it, very good. Nobody complains, right? But it is okay to have this kind of system, provided you are within your design limits and design requirement, right? So this therefore is a very important aspect in system design, that such a behavior is acceptable. Why? We will see later as we go along. So this is one important aspect, ability for generating torque. The next one is speed of movement. It should be capable of moving at whatever speed you want it to move, right? Having said that, now let us say that you want ultimately this robot arm to go from here to there, right? How much time you would like it to take to go from here to there? Do you want it to move in 1 second, or do you want it to move in, let's say, 15 seconds? How will you determine that? The weight of what we are moving definitely has to be considered, but how long it is going to take to move from here to there is usually an operational need. For example, if it is an assembly line and you have objects that are moving along a belt, and this robot has to pick this up and put it in a box, right? So this is one of the things in an assembly line where you want this entity to assemble the output, the end output. You need to lift it and put it in a box, enclose it and send it out for dispatch, right? So this is one application. So you want this to take it out, put it in a bag, and this entire operation of taking this from here, locating it in a box and bringing the arm back must be finished by the time the next object comes. Otherwise, it is going to miss an object. So you need, if you have determined already the rate of movement of the belt, then you know how much time you have in order that this arm goes from here to there and then comes back. So that then determines the speed with which you want it to move. But usually, given a mechanical system, you don't foresee that you will require to move from here to there and bring it back in 1 second. That's too high a speed for a mechanical system. You can build such a system, but your actuation need will be very, very large. You are really looking at very fast movement. Faster the movement, more your actuation need, right? So usually speed, the end speed which you want to achieve in comparison to the motor speeds that are available to you would be rather slow. If you look at an electric motor speed, for example, right, you would be speaking in the levels of something like 1500 RPM. You don't want this robotic arm to move at 1500 RPM and keep it there, right? You will probably hit something. It's impossible to do. So you would be looking at a much slower speed. So now the question arises is, do you make the motor itself rotate at a slow speed, or do you make the motor rotate at higher speed and do something else to make your arm move slower? Is it feasible to make the motor rotate at higher speed and get the arm moving slower? How do you do it? Gears is one, right? So you are really looking at motor speed versus load speed. Whether you want it to be same or you want it to be different. So this is one important aspect in deciding what kind of motor you want it to be used.